from what we had done previously, we were writing using this formula, which is Taylor's formula, to write a Taylor polynomial. So let's just say we have n terms. That is this right here, p sub n of x, which is an nth order Taylor polynomial, which has a finite number of terms. The rest of it that comes after it, there's still more terms behind it. That's going to be what we call the remainder, and we'll use an r for it, r sub n of x. And together, these two things make up our f of x. F of x is going to equal the Taylor polynomial plus the remainder. Now let's think about what comes next. What comes right after this nth term? All of the derivatives keep going up by 1, all of the exponents go up by 1, and the factorial goes up by 1. So the next one in succession here should be the n plus 1 derivative of f at a times x minus a to the n plus 1 over n plus 1 factorial. And this right here is what we call the Lagrange form of the remainder. The remainder is our n plus 1 derivative. And I'm going to put a c in here, and just bear with me for now why there's a c there. I'll explain that more tomorrow. This is what's called the Lagrange form of the remainder, where c is actually going to be some value between a and x. We're going to deal with the c stuff more tomorrow. Now this is going to bring us to something called the remainder estimation theorem. If there exists an m such that the absolute value of the n plus 1 derivative at c is less than or equal to that m for every c where c is between a and x, then the absolute value of your remainder is going to be less than or equal to m times x minus a to the n plus 1 power over n plus 1 factorial. M is what we refer to as the maximum value of the n plus 1 derivative. So what this says, what this is used for, is if this is true for every n, then our series is going to converge to whatever your f of x is. So let's do some examples. For now, let's just try and see if we can calculate it. I want us to find the Lagrange form of the remainder for the function cosine x. I'm going to tell you a is 0 and n is 8. Since this is a nice cosine function, I'm just going to write it out. F is cosine, f prime is negative sine, f double prime is negative cosine, and f triple prime is sine x. And then it repeats. Okay, so if I want the 8th derivative, that would bring me 3, 4, 5, 6, 7, 8, and then my Taylor polynomial would end with a cosine function in there. But since we're trying to find the remainder, r sub 8 of x, so it's going to be the 9th derivative of f at c times x minus a to the 9th power all over 9 factorial. So really all I need to do is plug in what my 9th derivative is. And our 8th one was cosine x, so the 9th one is going to be a negative sine x. So I just plug that in. It's going to be negative sine of c, x minus a, so it's just going to be x to the 9th power over 9 factorial. This is our Lagrange form of the remainder. Let's do it for the function f of x equals to ln of 1 plus x. Again, let's choose a to be 0, n equals to 5. Remainder always comes from the n plus 1 derivative, so that means we need the 6th derivative of f at c times x minus a to the 6th all over 6 factorial. So notice that it's going to be 6, 6, and 6 here because it's always that next term. And it's 5. So I have to have the 6th derivative of f. And f is equal to ln of 1 plus x, so I need to keep taking derivatives. F prime of x is 1 over 1 plus x. F double prime, if we take the derivative of that, is going to be negative 1 over 1 plus x squared. Then take the third derivative, and that's going to be 2 over 1 plus x cubed. The fourth derivative is going to be negative 6 over 1 plus x to the fourth. The fifth derivative of x is positive 24 over 1 plus x to the fifth. So this could actually be written as 4 factorial over 1 plus x to the fifth, so that when I write my sixth derivative, I have negative 5 factorial over 1 plus x to the sixth power. It's a lot cleaner when you're writing this. It'll make my simplifying a little bit easier. So my remainder is going to be negative 5 factorial over 1 plus c to the sixth times x minus 0 to the sixth all over 6 factorial. R sub 5 of x equals to, I have a 5 factorial and a 6 factorial that can cancel, and it's going to leave me with a 6. So I have negative x to the sixth over 1 plus c to the sixth times a 6 on the bottom. Do you think you could write the Lagrange form of the remainder for the nth order Taylor polynomial? So I want to know what r sub n of x would be. We need to have the nth derivative of f. So looking at the pattern from above, we should have an n minus 1 factorial on top, 1 plus x to the n derivative, and since it's alternating negative 6, positive 24, negative 5, and so on, I know I'm going to have an alternating series, and it's going to be negative 1 to the n plus 1. And my remainder always comes from the n plus 1 derivative, so that means I need to plug in my n plus 1 derivative of f, times that by x minus a to the n plus 1, over n plus 1 factorial. It's the same thing that we've been calculating above. So what I need to do now is really just plug in this stuff for my n plus 1 derivative, which is going to make it negative 1 to the n plus 2 n factorial over 1 plus, and I'm going to write a c in here because I want f of c, 1 plus c to the n plus 1 factorial. Okay, and then on this problem, a was equal to 0, so that's times x to the n plus 1 all over n plus 1 factorial. Now, whenever you have negative 1 to the n plus 2 power, that's actually the same as saying negative 1 to the n power. I need to cancel and simplify something here. Do you see this n factorial and the n plus 1 factorial? And all you're going to have left is an n plus 1 on the bottom. Why is that? Let me write it over here on the side so you can see. N factorial means n times n minus 1 times n minus 2, and so on. N plus 1 factorial means you start at n plus 1, then times it by n, then n minus 1, n minus 2, and so on. Everything will cancel out from the top and bottom except for n plus 1. So I leave myself with an n plus 1 down there on the bottom. And I also have 1 plus c to the n plus 1 power. And then in my numerator, I have x to the n plus 1. So this is my general form of the Lagrange form of the remainder for this function.